We're reviewing for our final Ohio State test in science. This is going to be our 8th grade review. Buckle up and pay attention. The first thing we're going to be talking about is earth science. One of the first standards that we are going to be trying to remember is the composition and properties of Earth's interior are identified by the behavior of seismic waves. Do you remember where seismic waves come from? They come from earthquakes. Earth has an inner core and an outer core. It has an upper and lower mantle, and it has a crust. The layers are differentiated by the reflection and refraction of seismic waves. Remember, those P waves can go through everything. They just go slower through the liquid outer core, but the S waves, they have to be reflected. So S waves have a larger shadow zone. That's this area right here. Convection currents form from the heat released from the Earth's core, and the thickness of each layer can vary. Now here we can see the different layers that we have. First, we have the compositional layers. We have the crust, we have the mantle, and we have the core. And then over here, we have the lithosphere, and then the red is the asthenosphere. Then we have the mesosphere. We have the outer core and the inner core. Some things to remember while we're here. The least dense materials are on the outside. This is the least dense. And the core is the most dense. One question that you guys tended to not do well on was number 36 on that benchmark assessment. It says, glacial and volcanic processes have helped shape the landscape in Yosemite Valley. Select the boxes to classify each Yosemite Valley feature as a result of either glacial or volcanic processes. We know a lot about volcanoes and glaciers. I'm thinking maybe it was just vocab that got you kind of goofed up. Basalt flows, thermal geysers, bedrock striations, terminal moraines, and U-shaped in cross-section. I'm going to show you pictures of those because I think that's going to help. All right, for the first one, for basalt flows, this right here is basalt flows. That is, we have a volcano that has lava coming out of it. Next, we have our thermal geysers. Our thermal geysers, those are those hot areas where steam shoots out of the earth. And then we have our bedrock striations, also known as glacial grooves. Do you remember talking about glacial grooves? We talked about Kelly's Island in Ohio. And then we have our terminal moraines. That is right here, and it's when the glacier stops. This is a terminal moraine. And then this right here is our U-shaped valley. That happens because of glaciers. It used to be more of a V-shaped valley because of streams. And then when the glacier comes through, it evens it out and makes it U-shaped. Finally, we have a picture here of the S&P waves. We talked about this earlier. But if we have an earthquake that starts right here, the waves are going to reflect and refract out. And once they hit the outer core, the P waves are going to slow down and go through it like this. Okay? But then if we are the S waves, we are going to go around it, or we're just going to stop. So there are no S waves down here. That means that there's a humongous shadow zone because no S waves could hit in this area right here. And then for our P waves, they have a smaller shadow zone. It's just right here and right here. Because they can go through, they just are a little bit slower going through. Next, P waves tend to travel through solids, liquids, and gases, and S waves travel only through solids. P and S waves generally travel faster in rigid, dense rock, and slower in less rigid and less dense rock. Down here, we have our P wave. Remember, it pushes. Remember, we did that with the slinky. And then we have our S waves over here, S waves. And they tend to go like this. Those are our S waves. Now, this is really important. You're going to need to know this. When you see the S waves, notice how they stop when they get to the outer core completely. And the P waves, they get to 2,900 kilometers deep, and then they stop, and they slow way down. And then they slowly go through the outer core. Then they speed up a little bit and go through the inner core. Who is this guy? Does anyone remember? We have a song about him. This is Alfred Wegener. Alfred Wegener, and he discovered continental drift. We're going to learn more. We're going to go back and learn a little bit more about that. The Earth's crust consists of major and minor tectonic plates that move relative to Earth to each other. Fossil distribution, paleomagnetism, continental drift, and seafloor spreading contributed to the theory of plate tectonics. So Alfred Wegener, he started with continental drift, but it never caught on because he couldn't find a mechanism for why those continents were moving. So then we came up with the theory of plate tectonics. In the theory of plate tectonics, he said, they said that the Earth was broken up into these big tectonic slabs, and that the slabs were moving. Not just the continents, but the ocean plates and the continental plates were both moving. You can see we have different types of crust. We have the oceanic crust right here. And then we have the thicker continental crust right here. And then underneath the Earth, this right here, this is our asthenosphere. This is really thick. Let's make it thinner. The asthenosphere. And it's like silly putty. And we have these convection currents. As the magma or the silly putty like layer gets hot, it goes up, and as it cools, it goes down. And these movements are what help move the plates. Does anybody know what this right here is? When the plates are moving away from each other, that's called a divergent boundary. And that creates a mid-ocean ridge. And this tectonic plate is going this way. This tectonic plate is going this way. When this plate keeps moving, it is more dense under the continental plate. And right there we get things like a subduction zone, which also gives us trenches. There are 3 different types of plate boundaries, and we're going to talk about those in just one moment. We have our convergent, our divergent, and our transform. Do you guys remember the song that went with that? We're going to talk about that in a minute. Here's another picture of that divergent boundary. And this is the mid-Atlantic ridge because of seafloor spreading. And as this happens, the youngest seafloor is going to be right here in the middle. And these older areas are going to be pushed out. So the oldest crust is over here, and the youngest crust is in the middle. Okay. Here's another picture of subduction. We have this oceanic lithosphere. See the ocean? It is going to be subducting under the continental lithosphere. This is what we call subduction.